Hello and welcome to Mathematics with Simon. I'm Simon. So today we're going to look at a question from the Mathematics Olympiad. And the question is, how do you factorise a cubed plus b cubed plus c cubed minus 3abc? So the first thing that struck me is that this expression has a lot of symmetry. So if you permute a, b and c in any way, it doesn't change the expression. Which means that I think we're looking for factors that have a lot of symmetry. I think we're also looking for one linear factor and one quadratic factor, if you know what I mean, because this is a cubic in A, B and C. Although towards the end we'll question this, but for now we're looking for one linear factor and one quadratic factor. So the most obvious linear factor is A plus B plus C, and that's also completely symmetric. And the most obvious quadratic factor to me is A squared plus B squared plus C squared. So when you multiply this out, you get A cubed, B cubed and C cubed, but then you get a bunch of other terms that we don't need. So my next guess was then to take off AB, AC and BC, and again this is completely symmetric. If you permute A, B and C, it doesn't change anything. So if you multiply A plus B plus C by A squared plus B squared plus C squared minus AB minus AC minus BC, you get the terms below. There is 18 of them, right? Because it's there's 3 terms in the first bracket and 6 in the second, so there's 18 terms below. And then what you can do is to start to pair them off to cancel them. So you've got plus AB squared minus AB squared, plus AC squared minus AC squared, plus A squared B minus A squared B, plus BC squared minus BC squared. Maths is great fun, isn't it? Plus A squared C minus A squared C, plus B squared C minus B squared C. So all of those terms just cancelling. And when they cancel, we see we're left with A cubed, B cubed, C cubed, and then 3 lots of ABC. So this is just the right answer. So basically, from my instincts around symmetry, I just kind of guessed it. But then it's natural to say, okay, fine, but how do you actually get there? So here's a way of getting there. Firstly, this is the polynomial that has roots a, b and c. X cubed minus a plus b plus c, x squared, etc. This is the polynomial with roots a, b and c, which means that if we substitute in a for x, we'll get 0, b for x will get 0, and c for x will get 0. So now we've got these 3 equations at the bottom, which are all equations in a, b and c. So magically we just add the 3 together. When you add the 3 together, you get a cubed plus b cubed plus c cubed, looks hopeful, minus a plus b plus c times a squared plus b squared plus c squared, which is great. Then you also get plus a plus b plus c times ab plus ac plus bc minus 3abc equals 0. So if then we rearrange that, okay, this is how we derive it. That's derived from there. That's derived from there. Make sense? That's derived from there. I'm loving these colours tonight. And that's derived from there. That's how it's all derived. But then basically what happens is if we add a plus b plus c times a squared plus b squared plus c squared to both sides and subtract the other term here, a plus b plus c, ab plus ac plus bc from both sides, we get to this expression at the bottom, which basically gives us our identity. We're obviously pulling out a plus b plus c as a factor of the right hand side, which just gives us identity. So that's one way of showing it. Another way, which is awesome actually, is to express this as a determinant. So we write the original expression as a determinant. So this determinant is a cubed plus b cubed plus c cubed minus 3abc. It's quite quick to check. A times a squared gives us a cubed. A times minus bc gives us minus abc. Just keep on doing it. B times ca, well, it's going to be minus abc, isn't it? And then this is going to be this is going to give us plus b cubed. This c times cc is going to give us another c cubed, and then c times minus ab is going to give us minus abc. So this determinant is the appropriate expression, and I suppose in general if we're doing a factorization, if you can write the expression as a determinant, it's a great start, because then you can do some determinant-like actions. So number one, we add the second column to the first column, like this. We added BAC going down to ACB. Then we add the third column to the first column, and as if by magic, we get A plus B plus C in the first column. So we take that out as a factor. Then we have A plus B plus C. It's beautiful. It's shaping up, isn't it, into the answer. And then we calculate the remaining determinant, which you will find is A squared plus B squared plus C squared minus AB minus AC minus BC. So there's a pretty quick way about determinants. So lastly, we can actually factorize this further if we carry out the factorization in the complex numbers. So to be honest, when I was presented with this question, I would assume that that's a factorization in the real numbers, because the real numbers, you know, that's the default system that we really use. You know, the integers, the rationals, the reals. The complex numbers are marvelous because they're algebraically closed, but at the end of the day, the complex numbers are not a totally ordered field, so, you know, I would normally assume we meant the real numbers, but actually there is a factorization in the complex numbers, which is beautiful and is worth thinking about, which is basically, so if you multiply, if omega is the cube root of 1, and if omega is one of the complex cube roots of 1, because clearly 1 is a cube root of 1, but if omega is a cube root of 1, then you get A plus B omega plus C omega squared, and you times that by A plus B omega squared plus C omega. If you multiply that all out, you get the stuff below. A squared plus AB omega squared plus AC omega is pretty obvious. You just need to grind it out. It's just 9 terms. You see, and then you see A squared, B squared, and C squared. And then what we have is AB omega squared here and AB omega there. And because 1 plus omega squared is 0, so this is the sum of the 3 cube roots of unity is 0, because essentially that would be the x squared term in x cubed minus 1 is 0, and of course the x squared term is 0. So the sum of the 3 cube roots of unity is 0, which means that AB omega squared plus AB omega is just going to be minus AB, which is there. Then AC omega plus AC omega squared is just going to be minus AC, which is there. Then BC omega squared plus BC omega is going to be minus BC, which is there. So we see that these two multiplied together is A squared plus B squared plus C squared minus AB minus AC minus BC, which was one of the factors in our original real number factorization, which means that if we're going to factorize in complex numbers, A cubed plus B cubed plus C cubed minus 3ABC is A plus B plus C times A plus B omega plus C omega squared times A plus B omega squared plus C omega. Wasn't that fun and beautiful? Hope you liked it. If you do, please hit like, please subscribe and hit the notification bell. I'd love to hear your own ideas, and most of all, I hope you enjoy your mathematics.